Are we ready to get started?
We're ready.
Okay. Well, first of all, thank you to everyone who signed up and is here, and a special thank you to all of our panelists. I wanted to take just a quick moment to introduce fellow environmental partners. My name is Stacy Taruscio. I'm one of the co-founders of Fellow Environmental Partners, and we're just under a year old. It's been a wild year. We've gotten a lot accomplished, a lot of projects on the ground, a lot of research, and tons of educational events like this. For the year of 2022, because last year was so hectic, we really want to accomplish the goal of focus. And when we think about the limited resources that are available to address orphan oil and gas wells, that makes us think about how do we choose which wells we would like to address, and how do we really build strategy around, addressing this massive well count that's out there with the limited resources we have. And one of the best ways that we think about doing that is by measuring some of the potential environmental and social impacts that those wells may have. And that's really why we're here today. We wanted to discuss methane emissions. It's very much an emerging tech, very much a space filled with startups and a lot of different things going on, and it's sometimes hard to follow. We've got some great experts here with us today. I'm going to introduce Natalie Pekney, but before I do that, she's going to kind of lead the panel. Before I do that, I want to make sure everyone understands that this isn't an endorsement of any one company's product over another. These are all great products, and like I said, there's a ton of great things happening in this space. And so the purpose here is really to give you guys a higher level look at the menu of items that's available to you as either operators or any other stakeholder in this process or concerned with this issue, so that you understand the technologies out there and how you might use it for many different applications across the oil and gas space and even other industries. So Natalie Pekney is going to lead the panel today. Natalie is a PhD in environmental engineer on the geoanalysis and monitoring team in the Geological and Environmental Systems Directorate of the U.S. Department of Energy's National Energy Technology Lab, which we call NETL. I don't know if Natalie calls it NETL, but we call it NETL. She's out of Pittsburgh, Pennsylvania. She currently conducts air quality research as it pertains to fossil energy production and use. She's the technical portfolio lead for the NETL Research and Innovation Center's Natural Gas Infrastructure Program, which aims to quantify and mitigate leakage from midstream natural gas infrastructure by conducting field-based assessments and life cycle analysis of emissions, developing in situ pipeline monitoring technologies, testing advanced pipeline materials. She does a lot. She researches greenhouse gas and other gaseous emissions from various components and processes within the natural gas system. For example, Marcellus shale gas well pad, natural gas pipeline, orphan oil and gas wells, which is why she's here today, and any other kind of metering regulating stations. Natalie has expertise in direct emissions measurements, regional ambient air quality measurements and monitoring, source receptor modeling, plume dispersion modeling, concentration surveying and mapping techniques, optical gas imaging. She does a lot of different things and is very much the expert in a lot of those things. To go back a little ways, she received her BS in civil engineering from Case Western Reserve University in Cleveland. And usually when we're on oil and gas panels and things like that, you announce, a Texas, Oklahoma type university, and everybody yells something out and you're supposed to yell back. But I don't know what that is for Cleveland. So we're just going to say go Cleveland. She also has an MS and a PhD in civil and environmental engineering from Carnegie Mellon University in Pittsburgh, Pennsylvania. And her team have over a decade of experience in aerial surveying techniques for finding orphan oil and gas wells. They've been measuring methane emissions since 2015. She really has an incredible background and is an excellent choice to lead this panel and to keep us on track here. So thank you, Natalie. Thank you to the rest of our panelists, and let's proceed.
Thank you so much, Stacy. I'm going to go ahead and share my screen. Let's see here. Okay. You see my slides okay?
Yes.
Okay. Thank you again for the introduction, Stacy. I'm very happy to join everyone today. So we've got several different methods for detection and measuring methane emissions from abandoned wells that we're going to be telling you about today, and we've divided them up amongst the presenters. So I'm going to be specifically talking about high flow sampling and gas composition analysis. And after a discussion yesterday, I'm going to add in there optical gas imaging too. So as Stacy kind of gave a little disclaimer, I'm a federal employee. I have to throw this up here that I'm not endorsing any particular product or company, but I will be mentioning some, some company names and some actual products. So one thing that I want to stress before we start talking about the measurement approaches is that when we encounter abandoned oil and gas wells out in the field, we've seen a big variety of what's been left behind. So sometimes you'll find a well has, just been completely removed everything from the surface, and all that's left is maybe a hole in the ground, like you can see in the pictures. You might see visible casing, or it could even be buried.
Hey, Natalie, could I interrupt you for just a moment?
Yeah, sure.
So sorry, do you mind putting it in presenters mode? It's a little hard to see some of the words. I think it would.
Oh, okay.
Do you mind making it a little bigger?
Yeah, let's see. I'm not quite sure how to do that because all I see on my screen, maybe switch windows. No. Well, this is a little different in Zoom for me.
Yeah, that's fine. I just wanted to give you the chance if it was showing up differently on your screen. So.
Yeah, I'm sorry. I just have the one laptop today instead of my multiple screens. So it's a little different for me to figure out. All right.
It's okay. Let's go ahead.
Okay, I apologize about that.
Okay.
All right, there we go.
No problem. If you go up to the slideshow on the menu, it might be there.
No, it stopped sharing altogether. I don't think I did that. Oh, I apologize. Somehow my whole PowerPoint presentation got closed, so I'm gonna have to reopen it.
I'll just take this time to mention the Q&A is open. So please, as you have questions going along, we would really like to answer those. So at the end, we'll have a little bit of time, 15 or 20 minutes, hopefully, that we'll get to those.
Yes. Natalie, sorry I threw you off there. I was trying to help.
Oh, no, it's okay. Having technical issues is kind of par for the course with, since the pandemic seems like it's always something. Right. Okay, let's try again. Let me see, am I still sharing?
I can see your slides.
Okay.
Yep. And if you want to go up to the slideshow at the top.
There we go. Okay, so back to the pictures of the wells. Some of them still have left behind a wellhead in place, and some of them even might have a pump jack or various other infrastructure left behind. So when it comes to figuring out how to measure the methane emissions from a well, one approach may not work at all configurations of the well. Sometimes we need to use something that can consider the fact that the well is buried. Other times, there's all kind of infrastructure attached. So we need to make those considerations when we go out in the field and try to collect emissions measurements. So high flow sampling. This is one approach that we have used since we started doing this work in 2015. On the market, there was a high flow sampler manufactured by Bacharach. And what it does is it actually measures methane flow rate, which is nice because there are lots of instruments out there that measure methane concentration, but we were after what is the actual emission rate from the wells. So the way that high flow sampling works is that you are using a blower to pull in a large volume of air around the leak such that you capture all of the leak along with some background air. And then there is a background probe that you can see me holding in the picture on the left there that you hold away from the leak so that you can do a correction for background. So that gives you the leak rate of the leak rate of methane from the source. And this back rack unit has two different types of sensors inside the backpack part, which are catalytic oxidation for lower concentrations of methane and thermal conductivity for higher concentrations. So this unit was really useful for us. It has various attachments that, the hose that sucks in the sample, you can put different attachments on there. You can see a wand kind of like one on the picture on the right. There's a plunger looking thing that we've used a few times. And there's also even a bag you can put over a whole wellhead. So that's been pretty useful. However, the back rack model is no longer being manufactured or supported. And it was kind of for a while the only game in town, the only system like this on the market. But very recently, we found that there are some companies that have been developing a high flow sampler for use. And this may have stemmed from a project that was funded from CARB that's being executed by Colorado State by Dan Zimmerly and Matt Harrison, where they're working on an open source prototype for a high flow sampler. So the idea is to make available to anyone the kind of like instructions for how to build one yourself using off-the-shelf components.
Hey,
and
Natalie,
some companies, yes.
Sorry, on our screen, we're not seeing it advanced past disclaimer.
Oh, I don't know why. I'm seeing the next slide.
Okay.
How about now?
No.
Why would it do that?
So
that's really odd.
If you click on slide 3 on the panel on the left, does it advance?
So I just clicked on the slideshow view.
Interesting.
That worked.
Here it goes.
Okay, so are you seeing the slide that says high flow sampling at the top?
I see one that says variety of well configurations make measurement a challenge.
Okay, I've already advanced to the next slide. So maybe there's just a really long delay.
Maybe there's a lag. Okay.
Okay, that's odd. Well, I'll just keep talking and hopefully the pictures will catch up.
Sure.
Sorry about that. So anyway, I'll just, not that I'm endorsing any of these companies, but there are 3 different companies I'm aware of, Sensors Incorporated, Het Tech Solutions, and AdGlobe. All 3 of them are coming out with a high flow sampler on the market. And so hopefully there'll be options, other than those of us that still have a back rack unit that we're using, there'll be options for others to potentially purchase a high flow sampler that will work as well or maybe even better than the back rack unit. So with high flow sampling, the cost is somewhere in the neighborhood of $40,000 for an instrument like this. However, this is just a snapshot measurement at the well. You're just taking a measurement at one point in time. So if you want to get some idea of the temporal variability, you have to go back and take repeat measurements or set the high flow sampler up to measure continuously, which it may or may not be able to do. Detection limits are a little higher for the back rack unit. Something like 0.05 to 8 cubic feet per minute. I don't know about the other companies, but I know the Semtech, the Sensors Incorporated version, has much improved on that detection limit, so it can get down to 0.001 CFMs, which is great. And this type of system has, it's very portable. It's very field portable. You just carry it in a backpack, go out to the field. It's battery operated. You can calibrate it with lecture bottles before and after your field work. So we found it very easy to use. And it's effective for many well types because of the different attachments you can stick on the hose end. So this has kind of been like our workhorse approach for measuring emissions. Just real quick, I don't know if you can see this slide, but I will mention that in our results we're seeing, and this is something that others report as well, very much a fat-tailed distribution where we go to most of these wells and we're measuring no or very little methane emissions, and then there's a small number of wells that have high emissions. So this is the type of source we're trying to characterize. It's pretty challenging to find those super emitters. Gas composition analysis is something else that we have done to get a feel for, what exactly is in the emissions other than methane. To do this, we've taken airtight gas syringes and collected a sample at the well. We also have a method that I don't have a picture of, but to use a sample pump to fill up a bag that we can take back to the lab and measure with a gas chromatograph. And what we've done in our gas composition analysis is mostly just look at other hydrocarbons like ethane, propane, butane, pentane, etc. Others may be interested in H2S. This is something that we haven't done before, but in some fields, H2S is an issue. And so there might be a need to collect measurements for the concentration of H2S. What we found briefly is that in the samples that we've collected, and I'm showing a table right now, but generally we found that something like 97 to 98% of the gas is in fact methane, and the proportion of other gases is very small. So we intend to continue collecting these gas composition measurements at other wells across the US to see if this is a trend that we observe kind of everywhere, or these samples that we collected were mostly in Pennsylvania and Oklahoma. So we'll be continuing to take these gas composition measurements. And then lastly, I'll mention optical gas imaging. We've used an infrared camera to help us kind of see emissions from the well. So with an infrared camera, you can view hydrocarbon plumes and then, get a sense for where the emissions are coming from, or if whether or not a well is leaking. So this is more of a qualitative rather than a quantitative approach. So we can look at where the leak is occurring and then focus the quantitative measurement techniques on that spot. So like for instance, with a well that has a wellhead in place and there are various pipes and flanges and things still present, you can check each of those spots with the infrared camera, find out where the leak actually is, and then take the measurement at that location. And I doubt you're actually seeing my slides right now because of this delay issue, but I do have a video of infrared camera image that shows us recording in a well. And when we do see plumes coming from a well, they're usually pretty faint, just like smoke coming out. And you can kind of get a feel for the fact that these wells, yes, they're emitting methane, but it's generally at a pretty low rate that can be hard to detect and hard to see. So I've described to you a couple different techniques we're continuing to refine and improve upon. So I'll end my part of the presentation there, and we'll let the other presenters talk about some other approaches. So we're going to start with Mary Kang. Dr. Mary Kang is an assistant professor in the Department of Civil Engineering at McGill University. Her research focuses on climate and environmental impacts of oil and gas development and groundwater hydrology. Her current projects are on characterization and mitigation of methane emissions from abandoned and marginal oil and gas wells and other oil and gas infrastructure. Previously, she was a postdoctoral fellow in the Earth Systems Science Department at Stanford University. She received a PhD in Civil and Environmental Engineering from Princeton University, a Science, Technology, and Environmental Policy Certificate from the Woodrow Wilson School of Public and International Affairs, and a master's and bachelor's in civil engineering from the University of Waterloo. And in between her time at Waterloo and Princeton, she worked as a water resources engineering consultant based in Reston, Virginia. So Dr. Mary Kang has extensive experience in measuring emissions from abandoned wells. So Mary, if you want to go ahead and share your slides. She'll be talking about flux chambers.
Great, thank you for that. Thank you for the introduction. So I'm just going to, I didn't have, I was trying to really keep it to 5 minutes. So I just have 3 slides. I wanted to start by showing some data just so that we can provide context for what we're trying to measure. And I know that the focus here is abandoned oil and gas wells, which include orphan wells. And so here I'm presenting data that has been published, including those by Natalie, but others at Nettle, and also Amy Townsend Small and others. And what's shown here are the range of emission rates that has been published so far. All of these publications are measurements that have been done in Canada and the United States. There's also work that's been going on abroad, some of which I'm involved in right now. So I think the key point that I want to take is on the top, you have positive values, so positive methane flow rate. So these are methane emissions to the atmosphere. The negative numbers on the bottom are methane sinks. So, methane is being pulled out from the atmosphere, and often due to the activity of methanotrophic bacteria. So I think the point here is that there's a large range of methane emission rates observed at abandoned oil and gas wells. And they can range from negative emitters and high emitters for abandoned wells. So, high emitters, what the definition of a high emitter is, it depends on the source. So for abandoned wells in general, it depends on the unit that you want to use, but 10 to the 4, 10 to the 5, 10 to the 6, these are all would be generally considered high emitters or within that fat tail that Natalie mentioned. So one more point that I wanted to make here, depending on what your objective is, you may want to use something different. The question is, do you just want to capture the high emitters, or do you also want to understand these low emitters and even negative emissions? Just one more point along this line, which is very similar to what Natalie mentioned about different methods needed. She covered the whole issue with the different above ground infrastructure and how you have to customize depending on where you are. And this is definitely definitely true in the measurements that I've done across the United States, Canada, and abroad. But also, I do want to say that these methods are not specific for abandoned wells, but can be used in other active wells. Here, I'm just showing some data for marginal, and marginal is an active well, but a low producing well, and also an active well, and measurements that were just conducted in Ontario, Canada. So there's more than just the abandoned oil and gas wells. These methods could be broadly applicable to other sources. And some of the things that you may want to think about is whether it's plugged or unplugged. That could really change your infrastructure. But of course, even among those categories, you have a wide range of well sites with different characteristics. Another thing I wanted to mention is in this study, we measured hydrogen sulfide. Hydrogen sulfide is a very toxic gas. So we had to develop a special methodology so that we can measure these wells emitting hydrogen sulfide. There are quite a few wells across Canada and the US and globally that have H2S. What's shown here is that we measured, so it's not a big data set. So this is in this figure. I don't know if you can see my cursor or not. Can you guys see my cursor? Okay, so there's among these abandoned wells, there's 2 wells where we measured. H2S, not just detected it, we actually measured the H2S emission rate as well. And what's interesting is they're both in, so we have to remember this is actually in orders of magnitude, the scale here. So the higher emitting, both of the ones that have H2S or emitting H2S are in the vicinity of the higher emitters. So there is, so we found this very interesting. So the point here is that you may need a different method depending on whether you have, a different surface and above ground infrastructure. And also depending on what kind of gases you have present at the well site. So this is just the last slide. The primary method we're using in our lab are flux chambers. However, we also do atmospheric measurements and inverse modeling to do methane emission rate quantification. I just want to add that I'm not necessarily endorsing any specific equipment here, but these are the equipment that I have, and this is what I'm routinely using in the field. So in the field, we have the Picaro gas scouter. So it's CRDS technology. It's really good for measuring low concentrations of methane. We also have a sensitive portable methane detector, which does higher concentrations of methane. And so we would use these directly within the chamber and in the field. And we also take a lot of gas samples to validate measurements and do cross comparisons. So we have a GC, so gas chromatograph with a flame ionization detector. So that would measure your ethane, propane, butanes. You can configure it to do different things. Also have a gas chromatograph isotope ratio mass spectrometer. So this would give you, mainly use it for stable carbon isotopes of methane and hydrogen and deuterium. But I also have several Picaros for doing, which is all based on CRDS or technology. And that would be for methane, ethane, again, the stable carbon isotope of methane. I also have one for hydrogen sulfide. So low concentrations of hydrogen sulfide. I actually have several sensors for hydrogen sulfide that I'm not showing here today. That's a whole other topic, and that's probably deserves another slide, but I just really wanted to stay within 5 minutes. So I'm not presenting that, but I'm happy to dive into that in the Q&A. So on the right, you can see some pictures of the two main sensors that we take in the field, but we often take other ones as well. So on the bottom left, you see a kind of a idealized schematic, but depending on the site, we will often change things. So one of the things that we're doing is, according to well integrity literature, the leakage pathway along a well can be, of course, within the production tubing or the surface casing, but the annulus between different casing and cement, or the cement and the rock, these are all identified as important leakage pathways. So one of the things we try to do is try to get that leakage outside of the casing or gas migration to a certain extent, assuming that it's right next to the well. So that was one of the intents when we designed this approach, to not only just get the flow rate at the well, but just outside the casing. And so in our methodology, we typically make sure to enclose the soil just around the well. Of course, this does not necessarily capture gas migration to the full extent, because of course it could be much bigger. So it would depend on how big the chamber is and the extent of the gas migration, which is a challenging question in itself. I don't know how I'm doing for time, but I guess I'll stop there. While I'm on the topic of well integrity, I think that's something that I'm very interested in. My background's in geologic storage of carbon dioxide, modeling multi-phase flow through porous media. So, doing reservoir modeling and such. So this is, so I really am interested in understanding the subsurface pathways and processes that contribute to leakage as well. And I'll stop there.
Okay, great. Thank you, Mary. It's really informative. I hope everybody's getting a sense for how there are multiple ways to come at this problem. It's definitely a challenge. So let's go ahead and move on to the next panelist, David Stewart. He's the Vice President of Customer Success at Environmental Solutions. He's responsible for developing and maintaining strategic relationships with external clients to enable customer success and drive ESG performance excellence. Additionally, he partners with the operations team and product development team to provide meaningful feedback for continuous improvement in their products. Before joining this team, David worked in the oil and gas exploration and production sector for 16 years, most recently as Vice President of Environmental Health and Safety and Regulatory for Crestone Peak Resources. And then prior to that, he served in senior leadership roles at Bonanza Creek Energy and Encana. His technical background includes an additional 14 years working in air quality and environmental consulting. He holds a bachelor's degree from Coe College and a Master of Science in Environmental Policy and Management from the University of Denver. So I see you've already shared your slides, David. So thank you. Go ahead and get started.
Thanks for the introduction, Natalie, and welcome everybody. Good morning. So I work for Project Canary, so I am endorsing a specific technology here, unlike the previous two speakers, but I think I have some exciting things to share on this topic. And I think the main thing is that with this slide, plugging and abandon programs, a lot of times we just plug and abandon a well and don't measure the emissions that are reduced or verify that it's truly plugged and there is no emissions. So really happy to see this webinar going and excited to present our solutions for ensuring that these are plugged properly. A lot of words here on this slide, but I'm just going to run through them quickly. We provide high fidelity gas analyzers that can be used in a variety of ways to find, measure, and verify proper plugging. We just acquired a new company called Aris Technologies, which is super exciting for me, as my background is in air quality. And these new tools that Aris Technologies has put together are very impressive. And I'm going to talk a lot about them today. But know that we're still integrating this new company into Project Canary, so there's more work to be done there. So, but basically, the new hypersensitive gas analyzers, they find wellbores fast. They can also differentiate between biogenic and thermogenic methane on the fly. These can be drone mounted, they can be mounted on ATVs, they can be even mounted quickly in cars and trucks, and also fixed systems to provide a broad range of approaches. Everybody today already spoke to the variety needed to approach this issue, and I think the Aris technology sensors, as well as the Project Canary X monitor, both provide unique solutions to the issue. We also have a data analytics platform that's used to log the data, trend the emission concentrations. It can be used for source attribution and quantification of leak rates. And then our Canary X methane gas analyzer is very effective at continuing to verify that the well has been successfully plugged. Our value chain is traceable, and the emission elimination from the P&A, we're working towards gaining methane performance certificates as part of our P&A process. This is a picture of the Mira Pico series. You can install these in a variety of different ways. The Lab in a Lunchbox is simply a handheld device that you can walk around with. The Ultra series is similar to the Pico series, except it has a very low drift due to the temperature stabilized optical core. And it also has quite a long battery life, 2 to 3 hours. And the Strato series is the drone-based version of the same sensor. It's very small, very light, and it can fly for up to 1.5 hours. And the detection limit on these Picos is roughly down in the 0.4 part per billion range, so extremely accurate. And they're being used not in oil and gas applications currently, but we're going to adapt these products for use in P&A. And really, the products themselves don't need any adaptation. It's just the use case for using them in a different way than they're currently being used for. But this picture here is really interesting. It's not specifically to P&A wells, but it's to a project that Aris Technologies has done with car-mounted sensors. And as you can see, the green identifies where methane leaks are, and the red is ethane plus methane. So if you do see the ethane in our gas analyzers, then you know it's thermogenic, meaning that it's originated from hydrocarbons. And this is a spec sheet on our Canary X monitor. Really, it's detection limit is the thing I'd point out at 0.4 part per million methane. We have these installed on hundreds of sites across the country, typically monitoring production locations, but also midstream applications currently. And these are now going to be used for our plugging and abandonment work that we're embarking on. So this is another picture that I just wanted to share with the team, with the group here. It's our quantification dashboard. Again, the site in the bottom is not a plugging and abandonment site, it's an active production location, but the exact same quantification tool can be used on a plug and abandonment site, whether it's plugged, whether it's low producing, like Mary had on her slides. But basically what it can do is it can tell you where the emission's coming from and how much emission rate there is. All this is using Gaussian plume modeling with some fancy statistical variation on that. But basically this actionable data can be used to eliminate emissions from plugged wells. And it can also identify things that may be leaking nearby. For instance, you know, like Mary mentioned, if you have an annular emission event or something that is occurring nearby, you're going to detect it with our equipment and quantify it and know where it came from. So we're very excited for this variety of technologies that can be used as fixed base monitoring systems to give the actual quantification and verification that the wellbore has been plugged properly and is no longer leaking. With that, that's my conclusion. Thank you.
Great, thank you, David. I think it's great that, you know, as a researcher, we frequently want emission rates, but there are a lot of the tools that are easily available are more like, you know, is the well leaking or not necessarily yielding an emission rate. So I think it's great that with this set of products, we'd be able to do that. So thank you. Okay, let's move on to the last panelist, Ben Losby. He currently serves as the Operations and Accounts Manager at Bridger Photonics, where he manages North American operations for their state-of-the-art gas mapping LiDAR. After obtaining a degree in physics, he worked in the exploration, production, and refining sectors of the oil and gas industry in Alaska, Montana, and North Dakota. Prior to joining Bridger Photonics in 2019, he ran an optics sales and service company serving clients across the US. So Ben is going to tell us about the gas mapping LiDAR technique.
I appreciate that, Natalie. So gas mapping LiDAR is Bridger Photonics technology. We have all of our research and development facilities, manufacturing all up here in Bozeman, Montana. And it's really across the entire natural gas value chain, emerging as the next generation in how operators are both finding as well as quantifying their emission rates. And its use case in the abandoned well kind of approach is emerging, and it's been really cool to watch this evolve. Before I get to the abandoned well use case, I want to give you a quick snapshot of the production sector. Obviously, these are a different order of magnitude emissions associated with production wells, but the use case around these is great because, you know, we gather all of this methane emissions data without actually ever setting foot on the facility. And as it applies to these abandoned wells, that can become a real challenge if it's on private land. Just the access issues associated with this. If you can fly over the top and find these things, becomes a lot more efficient. Also, by flying, you can get a very large sample set to really, you know, capture what does that fat tail look like, where does it trail off. You know, Dr. Kang was highlighting, you know, the 10 to the 5 kind of milligram per hour per well range. In our experience, in the little samples that we have so far on abandoned wells, that's probably an underrepresentation of what is actually out there. So it's really exciting to see this whole field emerge. Quick talk on Exxon. You know, does this technology work? Exxon actually selected Bridger to go to the EPA for regulatory compliance on the production sector. So they extensively vetted us along with several technologies to make sure what we say we can actually do. This is a production facility example again, but kind of highlights the spatial resolution and imagery that we're able to provide to say, hey, your emission is coming from here. And I saw a question pop up in the Q&A, you know, can you resolve a well versus a neighboring facility's emissions? And we're able to have a 6-foot resolution on where it's coming from. And even if you have a complex emission situation, we can actually pinpoint all the various emission locations contributing to a commingled plume even. Tank batteries are a great example. We'll get 2, 3, 4 emission points coming off a tank battery, all combining into one gas plume. Our team can actually dive into those data sets and pinpoint, you know, it's tank 7, 11, 4 that are emitting. So The spatial resolution component to this is really applicable to abandoned wells. On the other end of the value chain, I highlight the SoCal gas type of work that we've done because this is a more applicable use case to the abandoned well kind of emissions ranges that you tend to find. So this is much smaller emissions compared to the production sector. But SoCal gas is flying Bridger across their entire infrastructure because as you're in population centers, the really small stuff matters. And our ability to find the real small emissions from the air is really the driver for their use here of the GML technology. All right, so onto the abandoned wells. Obviously, the challenge is you have to find them first. As both Stacy and Dr. Kang have mentioned already today, is that not all abandoned wells are created equal when it comes to emissions. And so this is a pretty straightforward example. This is from, according to the Texas Railroad Commission, this is an abandoned well in Texas. They're scattered all over. And it just turns out that this is pretty easy to find. There's a road that goes to it. That's pretty convenient. But you still have to send a crew out if you want to measure this with handheld devices or anything like that. A much better approach is, hey, here's these 1,000 wells. Which ones are worth our time? Go fly them all. And then you can really narrow in on which ones are emitting, which ones are emitting the most, and then really prioritize your resources to tackle those first. So that's a really easy access type use case. A more challenging scenario is where here's a forest, where's the emission? Where's the well even? You know, a lot of these abandoned wells are from the early 1900s when kind of the GPS wasn't so great. It was more of 100 paces from the old oak tree. Well, now there's an entire forest of oak trees that have since grown up around it. And so in this picture, you have no idea, A, how good the coordinates you have are, and B, where it might be coming from. So if you can cast a wide net with an aerial platform, figure out where it's coming from, and then prioritize at the end, and it turns out the emission is right there. So you have all these emissions emerging from essentially a forest that A, walking out here on foot or driving in with an ATV or anything like that is just not a reasonable ask for most, you know, to really gain that large data set of what's going on out there. If you just know the ballpark region of where it's at, you want to get a large sample set and really figure out where you really should dedicate your ground resources. You know, all the various technologies that have been shown today are on-site type technologies. Prioritize those efforts. You should really take a large sample set first, figure out what's worth your time, and then go tackle those directly. And that's what Bridger is really focusing on, is, you know, covering thousands, if not tens of thousands of these wells, figuring out what fraction of them have large emissions associated with them, and really, you know, allocate these mitigation dollars effectively. All right, I went on rapid fire there, and I hope to keep us on track. Really looking forward to the Q&A piece of this.
Great, thank you, Ben. Yes, let's get to the Q&A. I'm seeing a lot of questions coming in through the chat as well as the Q&A functions here. So let me start with, there were a couple questions for Mary. One being, let me see here. What is the price point for the flux chambers? And also for the wells that, let me see what the question was specifically. The wells that were emitting H2S, were they vented or unvented?
So I can start with the price point. You know, there's nothing really off the shelf that I've come across that works. There's a couple things. There are flux chambers for soil gas sampling that are off the shelf that you can buy. But, you know, just, I think the pictures that Natalie showed were really good. If you have very complex and large configurations in the surface infrastructure, those off-the-shelf chambers don't work. So we've always custom built the chambers. Actually, the actual material cost isn't so much. I mean, you know, it's really hard to estimate because every chamber is different and they have different sizes, and we use different materials, and we build a lot, and it depends on how many times you use it and such. So we typically rebuild chambers every year. And the other big cost is we test them. Every single chamber that we go out, we do a controlled release testing to make sure the numbers are right before we go out. And so we do a control release testing. And then so the gases and everything that goes into that control release testing can and the analysis and the people power to do that analysis and that testing. And those things are what makes things more expensive. In terms of, so whether you use a dynamic or flux chamber, a dynamic chamber, it's a little bit more expensive because you have a pump, but it's still like within a couple $1,000 range, you could get a decent pump. And then the other issue is whether you need a power source. So sometimes that could get more expensive. The other big costs are the sensors. So some of the ones that I'm showing you, the Picaros, are in the order of, well, depending on I think there are 100 and more than 100K Canadian. So, in the order of 100K Canadian for the Picaro backpack samplers. And then the small sensors are like 20, I think, I forget the exact number, in the order of 10 to 20K for the sensitive sample. Of course, the other lab. So the lab equipment is of course much more expensive, like GCI-RMS, so you're looking at hundreds of thousands of dollars and special technicians and such. So it really depends on what you're looking for, to what kind of accuracy. I'm actually really trying to be very accurate, and also making sure that I can get low emitters and even negative emissions right. So, and also do a lot of detailed geochemistry, because one of the things I'm really interested in is understanding the subsurface flow path, in addition to finding the high emitters and trying to characterize them. The other question was about hydrogen sulfide, and I don't remember the question. Can you remind me? I don't see it, or is it in the
it's
chat?
those ones that were they vented or not vented? The ones that were leaking H2S.
These are, I'm not sure what it's meant by vented or not. These were the ones that we looked at were not plugged, and they didn't have, if you mean by venting in terms of surface casing vents, no, they did not have those. If you mean by venting as in plugged and vented, as they have in Pennsylvania and some places are cool, no, it was not. It was not those either.
Okay, thank you. There's a couple questions I'm seeing about the number of emissions measurements that have been made across the US and Canada, and the highest emission rate that we've seen. So I'll answer that, and then other panelists can answer it too. So in our case, I think we've measured emissions from close to 600 wells now, and that's been in Pennsylvania, New York, Kentucky, Oklahoma, and Texas. And we're hoping to keep growing that number and going to other regions too, because some of the data that we've collected and that others have collected have shown that there could be potentially significant regional variations in average emission rates. And with respect to the highest emission rate that we've seen, this isn't published, but we did visit one well in Western Pennsylvania that the emission rate was 23 liters per minute. And I'm sorry, I don't have the conversion for that in grams per second or any other, but it was the highest that we'd seen by an order of magnitude from, the next highest emitter. So that one was pretty high. But as I said before, because it's a fat tail distribution, we go to a lot of wells where we don't measure any appreciable emissions. So big variety there. Any other panelists want to answer that question? How many measurements have you taken, and what's the highest emission rate you've seen?
Yeah, I could.
Oh, go ahead.
Sorry, go ahead, Dr. King.
No, go ahead. It's okay.
Bridger's also in the hundreds range, and yeah, it's. I know Dr. Kang had milligrams per hour on her plot, but we're up in the kilograms per hour range for some of these. So.
So
Mary,
yeah,
you want to add to that?
Yeah, there's definitely in the published literature up to, I think one of the highest one I've seen in the published literature is by Giuseppe Etiope, where he measured a well in Pennsylvania. And that was one of the earlier publications that came out in like 2013. And I think it was in the order of kilograms, but there was just it's just one well. So definitely there are wells that could be that high. There's in terms of the number of wells, so I've measured, I mean, I started my measurements in Pennsylvania as well. So I did measurements in Pennsylvania, West Virginia, Oklahoma, California, doing a lot of measurements here in Canada, including Ontario, which is what I showed you, which is very similar to kind of Pennsylvania. It has the same history with development starting starting from 1858. And I've measured some wells here in Quebec. We've measured wells in British Columbia, Alberta, Saskatchewan. I'm also doing a lot of work overseas as well. I'm measuring abandoned wells. And in terms of emission rates, I do want to say that it is entirely possible that we haven't found the highest emitter. But there's definitely, you know, there's a lot of wells in that 10 to the 4, 10 to the 5 range. And so if you add them all up, I think they're still very important to catch, because if you look at the total amount of emissions. So if I don't know if I can share a screen and show some estimates, but there is an estimate. They are included in the National Inventory Report in Canada and also in the Greenhouse Gas Inventory Report. And you can see estimates there. But we did some modeling analysis of all published data to look at various scenarios. And there are regional variations, and there's a lot of things to account for. But there's a huge uncertainty in upscaling these emissions at the national level.
Okay, great. Thank you, Mary. Another good question here. If different methods are used to make the measurements, are we comparing apples to apples with the results? I can start with a response and turn it over to others, but something that we did early on when we started taking these measurements, nobody else had done it before to our knowledge. Turns out Mary was doing it at the same time, unbeknownst to us. But so we were approaching this like, okay, let's try a few different ways to collect these measurements and compare them and see how well, see what works and what doesn't. So we did high flow sampling, we did flux chambers, we did just kind of a low tech bag type sampling, and some more qualitative type approaches too. And then we did some comparisons between the methods, and there's pretty high variability. I think that might just be characteristic of the emissions from the wells. Some of them that we've seen don't have a really steady emission rate. There's significant temporal variability. But overall, we were happy with some agreement that we got between the different approaches. I think there's still more work to be done on this comparison issue though. And that's something that at NETL we're proposing to do in 2022. We're working with some of the other DOE national labs on a large scale program for undocumented orphan wells to characterize them. And this is an effort that is funded by the bipartisan infrastructure bill that President Biden signed back in, I think, November. So something that we'd like to do is get a little more information about how well these different approaches compare, and what might be some sort of like standard operating procedures that we can use to recommend to state agencies and others that want to collect these measurements. So does anyone else want to add to that? About comparing different measurement approaches?
That's okay. I do, everything you said, I concur with you. I think the variety of methods out there do provide different quantification values. I think the essence of where we're going with this is doing a lot of work with METEC at the Colorado State University and proving out our quantification technology versus blind testing, which is ongoing currently. And then we're also going to be doing quantification testing and verification with METEC out in a field setting in May and June. And so that testing will really verify what we've done in the laboratory already, which is verify that our quantification is fairly accurate. It is very difficult to say that you can accurately quantify in all situations. There's situations that make it much more difficult than others. And given the variety of plugging and abandonment types that we're going to approach, you showed pictures of Forest Bend and other areas that have some of these wells. different techniques will yield different results, and some are going to be better than others in certain situations. So just a variety of approaches, I think, are necessary in order to quickly identify the leaking well bores and quantify the rates accurately. I do believe that the direct measurement that Dr. Pekney, mentioned has a lot of, it's closer to the most accurate measurement, because you are getting an actual flow rate from the back rack or similar high flow samplers. But the problem is, a lot of the times the source might not be aggregated enough to get the total emission rate. So other techniques may be helpful in getting those disaggregated sources.
I agree. Yeah.
One thing I might add. Sorry.
Mm-hmm.
So one thing I might add is, it really, the how good your quantification needs to be is likely your end use case. If you're taking this all the way to plugging to acquire kind of carbon credit offsets or something of that, you probably should have a really solid understanding and provable emission rate. If you're just interested in plugging these wells that are emitting, find the biggest ones and plug them. I think a tiered approach here of, large sample set with some type of aerial approach to figure out where you should dedicate your ground resources. Obviously, the labor associated with getting out to all these sites is not insignificant. And so really prioritizing those field efforts to then really get a solid quantification number, if that is needed in your use case, that's probably the approach that would make the most sense in my view.
Yes. Yep. Thank you. Another question for you, Ben, specifically is, what's the turnaround time on the Bridger technology, and how quickly do you get results?
Depends what you want to know. So all that plume imagery that I showed on that kind of forested slide, all that imagery comes across in real time in the aircraft. So really the use case there is for immediate safety notifications in the production sector. However, fast forward 24 hours, so the day after every flight, we'll actually send out that plume imagery in a GIS file to operators or clients. If you are interested in the actual quantification component, so how much gas is that, that requires a human to interact with that data and do that calculation. So that's on the order of 5 to 10 business days, depending on your priorities and kind of our total workload.
Great, that's impressive. Yeah, thank you. Okay, well, I know we went over time. We're coming up on 12 o'clock Eastern here. So I think we'll probably wrap things up there, even though I am seeing some other questions in the chat. So I believe that contact information for the panelists can be obtained through Fellow if you would like to further discuss anything that you heard about today. I'm sure the panelists are happy to talk about the various technologies. So I want to thank the other panelists, thank Fellow for inviting us all. I hope everyone learned something today, and have a great day.